Hi, welcome back to another video. Today we're going to be looking at these momentum questions from the 2021 paper. We'll start with the multiple choice questions. And question 1.4 reads, consider the motion of a small stone thrown vertically upward until it reaches its maximum height. Ignore the effects of friction. Which one of the following combinations of graphs correctly shows how the momentum P and the gravitational potential energy U of the stone changes with time? Okay, now we'll go through these questions, we can go through these options, but it would be best if we did them through equations. And I can show you how we do that now. So let's start with the momentum. We know that momentum is equal to mass times velocity. Though we don't have time in this equation, so we don't know the relationship between momentum and time. But we can rewrite velocity. Now, we know that velocity Vf is equal to Vi plus A times delta t. And we're choosing this one because this equation has time in it. So what we can do is we can simplify a bit. We know that's Vi plus, and if we choose up as positive, then we're going to get minus 9,8 delta t. Now we can substitute this into our momentum equation, giving us m into Vi minus 9,8 delta t. Let's simplify. So we can distribute. So m times Vi minus 9,8 m times delta t. Now, let's rewrite this in a form that we may recognize. So if we rearrange this, we can write this as minus 9,8 m times delta t plus m Vi. Now P is equal to that. Now P is on our y-axis and delta t is on our x-axis. So this follows a format of y equals mx plus c, where mvi is our initial momentum. So this tells us that this momentum time relationship is going to be linear. So that means we are between option B and option D. Okay, now we need to figure out the relationship between energy, potential energy, and time. So we know that potential energy, EP, is equal to mgh. Again, we don't know what we don't know the relationship between potential energy and time. So what we can do is we can, instead of h, we can replace it. We can say a delta y equals Vi delta t plus half a delta t squared. Now we can simplify like we did before. So delta y, which is h in this case, that's equal to Vi delta t, and then plus half and then minus 9,8 delta t squared. We can simplify just a bit further. Delta y is equal to Vi delta t, and then 0.5 times minus 9,8, that's minus 4,9. So minus 4,9 delta t squared. Let's substitute this in place of h. We're going to get EP is equal to mg into Vi delta t minus 4,9 delta t squared. Now, this 2 in the exponent tells us that it's not going to be linear, right? That's a quadratic equation, right? And a quadratic equation has a curve, like a parabola. So that means that the EP, or the potential energy versus time graph, is going to be curved. So that means our option is D. Okay. Let's move on. Question number 3 from the paper. Now question number 3 reads, a ball of mass 0.06 kilograms is thrown vertically upward from the balcony of a building 3 meters above the ground. The ball reaches a maximum height h above the ground as shown in the diagram below. Ignore the effects of air resistance. Okay, that's important. So there's no air resistance. The question reads, name the force acting on the ball while it is in free fall. So an object that is in free fall only has one force acting on it, and that force is the force of gravity. Okay, question 3.2. The velocity time graph below represents the motion of the ball from the instant it is thrown upward until it hits the ground. Write down the acceleration of the ball at time 1,02 seconds. 1,02 seconds rather. So an object that is in free fall, or an object that's moving through the air, when you're doing this VPM section, the acceleration of these objects is always going to be 9,8 meters per second. And since they didn't ask for magnitude, we also need to give the direction. So 9,8 meters per second down. Question 3.3. Consider the area A1 and A2 shown in the graph above. Write down the numerical value represented by the difference in the area A1 and A2. So the graph is a velocity time graph. So it's important that we remember that the area gives us the displacement. Okay? Now area 1 is going to represent the displacement of the object from the time it's thrown up all the way to the time it reaches the maximum height. So that's going to be area 1. Then area 2 is going to represent the motion of the object, or the displacement of the object from that top point all the way down till it hits the ground. So that's area 2. So what is the difference between area 1 and area 2? We know that area 1 plus 3, there's the 3, is going to equal area 2. That means that the difference between them, so area 2 minus area 1 is 3. So again, area 1 plus 3 is equal area 2. That means area 2 minus area 1 is equal to 3 meters. Okay, question 3.4. Calculate the speed at which the ball is thrown upward. Right? Let's write out the information that we know. Okay, so we know from the graph that it takes 1,02 seconds to reach the maximum height. So time is 1,02 seconds. If we choose up as positive, that means acceleration is going to be minus 9,8. And then we know at the maximum height, the VF is 0. So we know 3 quantities, and if we know 3 quantities, we can solve anything. So we choose an appropriate equation. The appropriate equation that we can choose in this case would be VF equals VI plus A times delta T. 0 equals VI minus 9,8 times 1,02. That means VI is equal to 10 meters per second. So it's about 9,996, but I mean, we can round it. So they said calculate the speed at which it's thrown. So speed is a scalar quantity. We do not need to include direction. So the marks will be allocated for the formula, for substituting, and then for your answer with units. Okay, let's move on. 3.4.2, calculate the height h. Okay, yeah, let's calculate the height h. So to calculate the height h, we can use what we said in question 3.3. So we can say that area 1 plus 3 is equal to area 2. Remember, area 2, remember, it's an area, but it represents the displacement. And in this case, area 2 is the height. This is the height. Right? So let me just, instead of writing area 2, let me write down h, because that is the height. Okay? Now, we can work out area 1, because remember, that is a triangle. Right? This triangle has a base of 1,02, and we worked out the initial velocity. We worked out the height. So basically, we can say that it's going to be half base times height plus 3. So let's work that out. So area 1, that's a triangle. So half of 1,02 multiplied by the height, which is 10, plus 3 is equal to the height. So we can solve for the height. The height is equal to 8,01, if I'm not mistaken. Let me just confirm on the calculator. It's 8,1. Right? Yeah, 8,1 meters. Okay. Okay, excellent. Let's move on. Okay, let's take a look at the last question, which reads, after hitting the ground, the ball bounces vertically upward and reaches a new maximum height in 1.1 seconds. Okay, so we need to let's draw a diagram to help us understand what's going on here. So the ball is up at the maximum height, right? And we know here the V is 0. Then it goes down, it hits the ground, and then it bounces up to some height. Okay, we don't know what that height is. Now we know that the height from the initial drop here, we worked it out, that's 8,1 meters. Okay, now we also know that when it reaches the maximum height for the second time, we know the V is going to equal 0 there. But we do know that the time it took for this motion is 1,1 seconds. Now what we should do, and the method I'm going to show you is using the difference in the heights. So what we should do is we should work out the height from here to here. So let's work out that height. Let's look at the information that we know. So we know that the V is equal to 0, so VF there. So for this motion right here, okay, we know that A is equal to minus 9,8. Remember, we chose up as positive right at the start. And we know delta T is equal to 1,1. Now, let's choose an equation. Now, we want the height. So we can say that, let's say VF squared is equal to VI squared plus 2A delta Y. Now, we don't know VI squared. So we need to work that out. So in other words, we need to work out the velocity that the object is leaving the ground with here. Right? So we can work that out. Let me show you how we work that out. So what we need to do is we can say that VF equals VI plus A times delta T. Now, we know that it's 0 at the top. We want the VI. We know A is minus 9,8. And we know time is 1,1. Now we can solve. So VI, if we solve for VI, we get VI is 10,78. meters per second. So it's leaving the ground here with a velocity of 10.78 meters per second. Now we can choose any equation to work out the height. So let's go with Vf squared, the one we had before, equals Vi squared plus 2a delta y. 0 is equal to 10.78 squared plus 2 into minus 9.8 delta y. Now we solve for delta y, and delta y is 5.93 meters. That means from here to here is 5.93 meters. Now, let's put this into context, right? Remember we said at the beginning that there was no air resistance, right? So if there was no air resistance, and if this was a perfectly isolated system, then what should have happened is that the object, after bouncing, it should have reached 8.1 meters, but it didn't reach 8.1 meters. It reached 5.93. That means some energy was lost, right? And that energy that was lost was because of the work done by the ground on the ball, right? And that is a non-conservative force. So we can use that. We can say that the work done by a non-conservative force is equal to delta EP plus delta EK. Now, when we're working out delta EP, remember delta EP is mg and then h final minus h initial, and then plus delta EK. Is there a change in the kinetic energy? Remember, it at the top of that motion, it was 0, and it hit the ground and came back up, and it stopped again at 0. So the delta EK is 0. So this is 0. Now we can solve. We know the mass is 0.06. That was given to us at the beginning. We know gravity. Gravity is 9.8. Remember, it's not 9.8 here, right? Because we're not using equations of motion here. Okay? Then the final height is 5.93. We worked that out. Minus the initial height, which was 8.1, and then plus 0. That means the work done by the ground on the ball was minus 1.28 joules. That's it for this question. That's it for this paper in terms of work energy power. And if you found it useful, please leave a like, share, subscribe. If there's something specific you'd like me to do or a specific question you have, please let me know in the comment section below. Until the next one, bye-bye.